So we've got a loss of methyl and this oxonium ion, and then we lose another ethyl group from that. So it's multiple, it's a product that arises from multiple decompositions. But you're right, it's like that. All right, NMR. In probably the C13 NMR is going to give us the best information because carbon, as part of an ether linkage, is going to be between 65 and 90. Okay. Hydrogens attached to ether carbons will be between 3.5 and 4, but there's an awful lot of stuff that appears in that region, so that's usually not awfully diagnosed. The bottom line here is that without mass spectrometry, it's pretty hard to know if you've got an ether. We don't have good evidence in the IR, and we don't have good evidence in the NMR. Evidence that's real strong. Now, here is something we've already talked about, which is kind of nice. We're going to look at the Williamson synthesis of ethers. And when you turn your quiz in, and I suggested another way might be better, has to do with the theory that we see here. In a Williamson ether synthesis, an alkoxide reacts with an alkyl halide, and this could be other leaving groups besides halide, to create the ether and the forced off or the removed halide. Could be bromide, could be iodide. Usually it's one of those two because they're better leaving groups. Here's the issue. This is an SN2 reaction. And so if I've got a choice between these carbon groups to make one of them an alkoxide and the other a halide, I'm going to pick the pattern that's going to give me an SN2 reaction. Does that make sense? So a primary halide is the best. Secondary halide might work, but not as well. Tertiary halide is not going to give me a reaction. Now, halides or tosylates work well for the leaving group. Now, here's an example. I'm going to make ethyl cyclohexyl ether. The way to do this is to start with the alcohol here and make the alkoxide from this, because this guy is a primary leaving group. Does that make sense? And so I'm going to get the SN2 mechanism I want. Did I skip a slide? What would happen if I started out the other way? I started out with my alcohol on the ethyl group, turned it into an F oxide, and tried to attack a tosyl cyclohexane. It would be, yeah, it would be, we would start getting away from an SN2 reaction. And one of the problems is that the alkoxide, once I take that hydrogen off and make it a base, or a nucleophile, it's a good strong base also. And if I've got a substitute of a secondary or tertiary halide, I'm actually going to make the alkene rather than the ether. The base is just going to take the hydrogen off next door, and with the leaving group taken off, I'm going to get an alkene rather than an ether. Okay. Here's another one. I've got, they don't give us these as problems here, but here's the ether I want. Where is the, methyl, and then this great big complicated guy here. Obviously, this guy is going to give me better results having the leaving group, because it's going to be an SN2 reaction, rather than having the leaving group here. Does that make sense? Now, how can I make alkoxides? We've actually had several reactions described. So if I've got an ROH.
We made them today in lab.
What's that?
Made an alkoxide in lab today.
There you go. What did you use?
What did we use? We added, I can't remember. What did we add first?
Did you make an alkoxide today?
Yeah, we were stirring it all alkoxide and we protonated it. Yeah, we did.
One reaction is with sodium metal.
What do we have? What is it? Oh, yeah, sodium borohydride. Oh, crap.
This is going to produce hydrogen gas. Okay, and we've talked about this one. Another one that can be used is sodium amide. And what do I get there?
I'm going to get ammonia.
Yeah, I get the alkoxide there. And ammonia, which with warming becomes a gas and we can drive it away. There's another one we've not really talked about, but it's useful here. Is sodium amide, or sodium hydride, excuse me, like that.
This is the, it's going to be against it.
Yeah. Gas. Now, and someone mentioned potassium, and that is a good choice here. If I'm trying to make an alkoxide from a bulkier alcohol, potassium is good for that. Better for removing the hydrogen of a bulky alcohol, like terpene alcohol, for example. Potassium is a better choice than sodium. Which do you think is harder to get your hands on, by the way, sodium or potassium? Potassium. Not only is it more rare, but it's more reactive, and so it's harder to maintain, more expensive to buy. But if you need it, you need it. By the way, here's the sodium hydride reaction we were just looking at here. Now, there are exceptions. Every rule has exceptions, it seems like. If I'm trying to make an ether that contains an aromatic group, I can't go just any direction. For example, if I want this ether here, I'm going to have to start with this guy. What if I try to do this? And we actually don't know the chemistry. What if I try to use this as the substrate in the SN2 reaction? It doesn't do substitution at all, as a matter of fact. Not SN1, not SN2. This reaction here, taking that bromide off of there, does not exist on our palette for aromatic compounds. Aromatic compounds are unique in that sense that they don't do the same kind of substitution reactions we've already seen. You don't know that yet, but now you do. However, this happens taking the hydrogen off of here and leaving the phenoxide on it behind is easy. I don't need to use sodium metal, sodium hydride, sodium amide. I can just use sodium hydroxide because that hydrogen is that acidic. And so, despite the fact that we're more limited in terms of our options, this part of the reaction is a whole lot easier. So I'm going to make the phenoxide, and then I'll put this in contact with the alkyl halide that I'm reacting with and complete the other half of the reaction. Does that make sense? Now, this gets to the point we were making. Here I'm trying to make this particular ether, okay, and there's really only one way to do it. If I make the propyl group the nucleophile, or the propoxide the nucleophile, I'm not going to get that ether because this is not going to be a SN2 reaction. What's going to happen here is the bromide is going to come off on its own in an SN1 fashion, and this guy is a heck of a base. So what it's going to do is it's going to take one of these hydrogens off and give me the alkene rather than the ether. We were talking about this a moment ago, but now we've got an illustration. There we go. Instead of getting the ether, I actually do an elimination reaction Bromine comes off one carbon, hydrogen comes off another carbon, and I get an alkene instead. Does it follow okay? So how would I do this reaction? It's on the next slide.
Probably flip them as well.
I start with the alcohol here
Right.
and make this the bromide or iodide or whatever I'm going to use. And that alcohol we were just talking about, this doesn't work as well with sodium metal, but it works pretty well with what? Potassium. Okay, because it's a bulkier alcohol. Here's what we're talking about. So I use the tert-butoxide as my alkoxide here. I use a primary bromide here, and I do get the SN2 reaction, and I get good yields of my ether. All right. Okay, this makes me tired just to look at it. We actually talked about this at one point in time, and I'm pretty sure that you probably don't remember. This is an alternate way to make an ether. And it's an analog or an analogous reaction to the oxymercuration-demercuration reaction that we use to make a Markovnikov alcohol. Do you remember that? You take an alkene, you react it with mercury 2 acetate, you get the 3-membered mercurinium ion, water comes in and bumps one of the mercury bonds off, and then I remove the mercury group with sodium alcohol. Remember that? And I get a Markovnikov alcohol. Let me way back when we do that.
Yeah, it'll be on our test plan.
Well, we can do something kind of exotic here. Instead of running this in water, we run it in an alcohol. And so I get the mercurinium ion, a 3-membered mercury group. So I've got mercury up there with an acetate coming off of it. Now the alcohol, instead of water, attacks one of the carbons, and I get that guy. And then I treat it with sodium borohydride to get rid of the mercury acetate group. And notice instead of a Markovnikov alcohol, I get what?
Markovnikov ether.
Markovnikov ether. So this is just a separate type of reaction that can be done with a reaction we already know, where the nucleophile that creates the addition product to the double bond is not water but an alcohol. An example here, 1-hexene. Get a mercurinium ion here, and then we use methyl alcohol. Alcohol is going to attack secondary carbon, the most positively charged carbon, and then we reduce the mercury off of the primary carbon at the end, and I get yields that are pretty darn good, 80%. Could I have done that with a Williamson ether synthesis? The answer is yeah, I could. Which end would I have started with as the alkoxide? This one or this one?
The more bulky? No.
This one.
Oh, it is, okay.
Okay, and maybe methyl bromide